Okay, so can gravity exert a torque? Okay, so if I support this sort of in the middle, whoops, pretty sensitive actually. But if I support it on the end, then it clearly wants to rotate. So let's see if we can figure out how gravity acts to produce a torque. So here's my eraser or my canonical physics blob of mass. Okay, and I want to consider a little chunk of my blob. And so that's going to be my little mass m sub I. And the gravitational force on that little bit of mass goes down that way. And I want to consider, let's say, the gravitational torque with respect to that point. So there's the axle, and we want to see how gravity wants to make this thing rotate. So as I told you, I could just extend the line of force of the gravitational force to get the perpendicular distance. That's the only distance that's relevant for computing the torque. So our perpendicular goes from the axle out to the line of application of the force. And instead of calling it r perpendicular, I'm going to call that the x direction. So that's x sub I that corresponds to the mass point m sub I. So the torque would be the sum over all the little bits of mass. I'm only showing you one, of course, of r sub I perpendicular times f sub I. But it's gravity, so f sub I is m sub I times g. And as I mentioned, I'm going to use that direction to be the x direction. Okay, so I just sum over all the little bits of mass, and what matters is only the x component. I don't care about up and down. That doesn't affect the torque. Once upon a time, we had the center of mass, which we found by taking the first moment of the mass and dividing it by all the mass. So this part is supposed to look awfully familiar. Yes. So x sub I times m sub I, but that's what's in there. G is just some crummy constant. I can pull that out of the sum. So I can just replace this sum with all the mass at x of the center of mass. Right? That sum is going to be the same, oh yeah, as all the mass. So this is the entire gravitational force for that potato or whatever it is. And it acts, as far as the torque is concerned, as though it's concentrated at the position of the center of mass. Okay? So an extended object gravitates as though all the mass is at the center of mass. When is this untrue? He says non-uniform density. Did I assume uniform density anywhere? No. Is this always true, or what? What's going to screw this up?
Gravity isn't uniform.
If gravity is not uniform, then I can't pull the G out. So when you're falling into a black hole, do not use this formula. Okay? Or severe damage may result. So do not use that formula near the horizon of a black hole. Christian?
The tau there looks like force times, the tau looks like the top.
Yeah.
Looks like force times distance, which I remember remember reading somewhere is like the moment. Is there any are they the same thing? The torque and the moment of a force about a point?
Excellent question. He says he's heard the phrase, the moment of a force. So in this case, we have a force, and the first moment of that force would be the product of the distance and the force, so it's a perpendicular distance. So it's exactly right. It's the same thing. So the torque is the first moment of the force. Great.